Howdy, I'm Aditya. I and my team, Kamal and Riddhi, are here to present our project, Spacecraft and Logistics Optimization for Long-Term Manned Mars Expedition. We have two disciplines involved in our optimization problem. One is regarding optimization of spacecraft, for which we consider Saturn V rocket as reference. By the end of our project, we modified the dimensions, volume, fuel, and payload capacities and developed Orbital Launch Booster OLB, which will reach low Earth orbit. Payload of this rocket is Interplanetary Vehicle IPV, which is used to travel from low Earth orbit to low Mars orbit. After reaching Mars, a lander is used to travel from low Mars orbit to Mars surface. We developed constraints regarding these rockets and payload. Second discipline in our problem is logistics optimization. Few modules are required to sustain life and to aid astronauts in their return journey. They are modules of food, water, life supporting equipment, lander, mass ascent vehicle, MAV, etc. Few modules have to be sent before manned mission and few after the astronauts reach Mars. The sequence is optimized. Total number of mission years and total cost of mission are determined by the end of our project. We develop the necessary constraints. We have two objectives. One is to minimize cost of mission, considering that all the desired supply and travel operations are possible. Other objective is to reduce the duration of the mission and taking care that all the supplies are delivered in shortest time span possible so we can send more number of astronauts. We have considered parameters like densities, cost, and volumetric ratios of fuel, parameters of standard components like mass and thrust of thrusters, dimension of different modules, inflation rates, fixed launch costs, etc. We have three constraints related to thrust, three safety constraints, eight geometric constraints, five transfer velocity constraints, and one constraint related to mass of payload. Components like food, water, equipment, etc. are considered as blocks of certain volume. It is assumed that this will fit in the rocket irrespective of shape and density is same throughout this volume. We have considered inflation of costs in future missions as 2%. Thrust actually varies with external pressure differences, but we considered it to be constant. The number of thrusters as in Saturn V. We assumed that maximum 2 missions can be done in a year, considering average time required to manufacture the rocket and travel. This slide explains the sequence of operations. In the first batch, Mars Ascent Vehicle MAV will be sent from Earth surface to Mars surface. Then the fuel required for MAV is sent to low Mars orbit, followed by the equipment which is required to be sent before manned missions. Now, a manned mission is done, and astronauts are sent from Earth surface to Mars surface. Resupply missions of life-sustaining equipment are done now. There are gaps between these missions during which preparatory missions for the next set of astronauts are performed. Now the previous set of astronauts will leave Mars and new set of astronauts will leave from Earth. This process continues. Here, inputs are the design variables. H1 to H3 and R1 to R3 are the heights and diameters of each stage. Mass of payload, heights of food, water, equipment, etc. As we consider these food, water, and equipment to be volumes, and the radius of this volume is RIPV. FRR is fuel remainder ratio, which is the ratio of fuel during transfer maneuvers. We have three main modules, one related to OLB, one related to IPV, and one related to MAV. And this module at the end is related to cost calculations. We have three submodules in each of the module. First one is related to fuel and components. Second one is related to mass. Third one is related to transfer velocities. By the end of our optimization, we will get total cost and total life as our outputs. This is the block diagram of our entire optimization process. The yellow blocks are the design variables. These are used in the process. We have a convoluted process in which all the design variables will be used and we get outputs. These can be subdivided into modules, module 1, 2, and 3. As we have seen in N-square diagram, Module 1 is related to OLB, Module 2 is related to IPV, and Module 3 is related to MAV. Here are the output calculations calculated, and we get total life and total cost as our outputs for our objectives.
Design of experiment. The bounds of the design variables are decided based on the Saturn V configuration and experimenting with them. To understand the behavior of the objective function, design of experiment has been carried out. Given the large number of design variables and considering the time required for each run, performing a full factorial in this problem would be infeasible. Therefore, to explore the design space effectively, an orthogonal array is necessary. For this formulation, from the formulation of this problem, there are three variables, namely H food, H water, and H equipment, which influence the output in the similar fashion. So to save time and computational power, these three variables are combined into one for the sake of design of experiment. And a Taguchi array of 13 variables and 3 levels has been conducted. The total number of experiments are 27. The constraints in this problem are ignored, and the mean of total cost in every experiment is calculated. And also the effect of design variable is also calculated. The best predicted design location is selected from the most desirable design variable, and the total cost is also predicted from this analysis by adding the mean effects linearly. Coming to the factor effects, the factor effects are plotted for all the design variables. These are divided into categories based on its impact on the objective function. The most influential design variable from this analysis is the FRR IPV, the green one over here, which decides the fraction of fuel required to reach from LEO to LMO. Moreover, the cost of fuel used in this maneuver is the highest, and this satisfies the intuition as well. However, this process cannot be assumed to be accurate for this problem because the constraints and the objective in this problem involve highly nonlinear terms. And moreover, to reinforce this assumption, the actual cost in this problem for the most optimum design variable from the DOE is different from the predicted. So this shows the nonlinearity as well. So however, this location is chosen as the starting point for gradient-based optimization. We observe that the optimum point obtained from the DOE doesn't satisfy the constraints as well, but however, it is taken. And we have performed sequential quadratic programming for gradient-based analysis. And this algorithm is chosen because of its because it uses separate methods depending on the design variable position with respect to constraints. Each run takes around 27 minutes to occur, and multi-start was employed within the bounds, and many runs were carried out. A graph is plotted which shows the convergence between the value of function and the iterations. One main thing to observe is that the constraints were scaled, which reduced the number of iterations by around tenfold. And also regarding the convergence from the graphs, we can see that it converges to various local minimas, but the local minimas remained within very close proximity with each other, indicating that the region surrounding the global minima has slight perturbations, but all lie within the same design space. And the most desirable solution among these runs is the final solution considered for now. And the total number of missions and the cost required, which come as output, is around $896 million per year. To validate the optimization carried out, we need to perform benchmarking analysis where we compare the results with the Saturn V rocket. So for this, Saturn V payload was given as an input to the problem, and the optimization was carried out. And one main thing to observe is that the total height of the rocket and the percentage of fuel with respect to payload is pretty close to the actual values, even though the other smaller parameters like the radiuses and heights of individual components varied, but overall it stayed pretty much up to the mark. And so this shows that the assumptions and the simplifications which we used in this overly complicated problem are reasonable. Coming to sensitivity analysis, which is performed at the optimum point obtained from gradient-based method. Firstly, sensitivity analysis carried out with respect to the design variables. It is carried out using the formula provided here, and in this formula, delta x by x is maintained constant for all the design variables, so that it is equalized in all the directions while calculating the sensitivity. And from the analysis, we can observe that the design variable called FRR-IPV, the fraction of fuel, that influences the most, and this is concurrent with the result obtained from DOE as the most influential variable. And after FRR-IPV, the radius of the two stages, the stage 1 and stage 2, are the most influenced on the output of this function. And later, moving on to parameters, cost of launch shows the highest sensitivity, and this also matches the intuition, as in each launch, this cost of launch is a very big value, and it gets added on and it gets multiplied as the number of missions increase. And coming to the constraints, for like as the intuition predicts, the constraint which has FRR IPV most is the most sensitive constraint or the most active constraint. So likewise, we get delta V5, the velocity maneuver required to go from low Earth orbit to deep space is the most active constraint, and changing this constraint by quite a small amount, like 100 meter per second, changes the whole optimum value and changes the overall cost around $27 million per year. And calculating the sensitivity with that, it gives around 1.4, which is a huge value, which is greater than many design variables sensitivity as well. Moving on to heuristic methods to optimize the algorithm near the local points and to effectively scout the design space, genetic algorithm was employed. In this genetic algorithm, we used tolerance of 1e minus 20 and the population size of 300 in order to effectively tune it, because at the start it didn't give the results predicted by FMINCON also, but after tuning it was very effective. And after optimization, various runs were carried out, and a graph is plotted between the value of function and the generations. And looking at the graphs, we can see that it doesn't, even this algorithm doesn't converge to a single point, but it converges to small minimas. But one great thing about this algorithm is, when compared to SQP, is that the places at which the convergence occurred, the design variables are within more closer proximity than SQP. And this shows that genetic algorithm is more efficient than SQP. So various runs were performed and the best result was obtained similar to what we did in SQP. And the outputs from this problem are around $888 million per year and 35 years. So comparing that with SQP, a total of $7.9 million was saved, and there were small changes in the design variables as well. We also performed scaling for this. Um, the Hessian was calculated from the FMINCON function. It wasn't done by hand because of the nonlinearity and the complex variables involved. The first 6 variables were scaled and the rest were automatically scaled in the problem. And when these were scaled, we didn't observe any changes in the final result, but however, the number of iterations was reduced by half. So this saves computation, but overall MATLAB solver is powerful enough to handle our specific problem.
Our problem has two objectives. Our main goal is to minimize the total cost of mission per year by minimizing the total cost of fuel per year. And our second objective is to minimize the total number of mission years. We have imposed constraint on the total mission duration to be in the range of 15 to 35 years. Since the two objectives have to be optimized simultaneously, a weighted sum approach is employed in the genetic algorithm in order to perform multi-objective optimization. Various runs were carried out by changing the weights assigned to both the objectives. Since our second objective is a discrete function, final result did not vary significantly for some weight combinations. For 5 weight combinations mentioned in the given table, a Pareto front was plotted, as you can see in the left figure. For the combination of weights which gave the least output parameters, the genetic algorithm was carried out several times to ensure that the value obtained was close to the global minimum. From the table shown here, we can understand that the cost of fuel per year steadily decreases as more weight is added to it, and the converse effect is seen on the number of mission years. This observation reinforces the statement that the objective functions are mutually opposing to each other. Design variables have a huge impact on the final objective functions. From the 5 solutions, we have selected the second solution with number of mission years equal to 31 years. Keeping in mind the discrete nature of the second objective, an attempt was made to explore the convex regions of the Pareto front. In this, we use an indirect method where we fix the value of the second objective and run genetic algorithm a couple of times to minimize the objective function. This was done with all possible values that can be assigned to total mission duration objective, and corresponding cost functions were recorded. This data was then plotted to get a Pareto front. We observed that all the points obtained by the weighted sum method were also present in this Pareto front. The scattered points are not found anywhere below 15 mission years or above 35 years because of the constraint imposed on the number of mission years. This method endorses the weighted sum approach as no new points in the non-convex regions are discovered and the final results remain unchanged. To conclude, I would like to go through some of the features of our problem. Our problem is multidisciplinary and has nonlinear objective functions and constraints. Had it been linear, the optimum could have been found just by performing DOE. But for our problem, DOA is not sufficient to optimize the problem. We were sure of the obtained optimum being closer to the global minima after implementing sequential quadratic programming with multi-input start. The computational time was significantly reduced when scaling was performed on constraints. However, scaling of design variables did not affect the computational time a lot. In all the cases, there was consistency in the final results that were obtained. Genetic algorithms give better results as compared to the gradient base since it used multiple start points that were distributed all over the design space. Then multi-objective optimization was carried out using two methods. First, the weighted sum approach, and second, a problem-specific approach. From the weighted sum approach, 5 solutions were presented. Our recommended solutions suggest a mission of 31 years duration with cost per year as $940 million. In future, we can use other heuristic methods like particle forms, simulated annealing, and the bounds can be reduced so that we have a smaller region to explore. This might give better results. Packing of payload in IPV can be updated according to the actual equipment measurements and distribution to get some realistic results. We can also implement this method on different configurations of rockets depending on the purpose of the mission. Orbital mechanics of the problem can also be taken into consideration. We can also implement slingshot transfer mechanism, which might lead to some reduction in the total cost. We can apply similar methodology for Moon, considering as a base, and missions between Moon and Mars can be optimized. These are some of the references that we have used while working on our project. That's all from our side. We had a lot of fun while doing this project. We thank Dr. Allaire for giving us this opportunity, and we'll be happy to answer any further questions regarding our project through emails mentioned in the slide. Thank you.